Hello, good morning everyone. I hope everyone has joined by now. So, can you please let me know how many of you have read those three PDF files that I sent? They were on boundary layer, pipe flows and pumps, and MPSH. Or you can write which one you have read and which one you have not, so that we can decide how to proceed today, what to discuss, what not to discuss. Okay. It seems like only some of you have gone through the reading material. Yeah, so what we'll do today is that um, we have one assignment remaining. That will be the final one. So you can again have a look at all three PDFs, and then we can have a test, or you can call it take home assignment, take home exam kind of thing. We can have it day after tomorrow or Thursday. What would you prefer, Thursday or Wednesday?
Sir, can you repeat what you told us now?
Okay, so I'm saying that because not many of you have gone through this, so there is not much point in discussing these today. So what we can do is you can go through these, and we can have, I can give you an assignment today or tomorrow, which you can submit by Wednesday or Thursday, that is 25th or 26th. So it will be like an exam, take home exam, and you will get 2 or 3 days to complete it. And it will be based on these three topics.
Thursday, fine, sir.
Yeah.
Sir, and I have one doubt.
Yeah.
Actually, I want to know the what pattern you will give in the 20% NSEM. You can you
There
tell
is no
that?
end sem for this course. We'll
Okay,
just grade you based on these assignments.
okay, sir.
Yeah. Okay, so this will be the final assignment. So let me discuss the remaining topics today. And some part of what is there in the PDF on pumps. So we can start with that. Yeah, there is not much left, and we won't go into much depth also. No. Yeah, there will be no NSEM exam. There is no live exam. It is just assignments. Okay. So pumps, fans, blowers, all of these come under fluid moving machinery. Generally speaking, there are two kinds of fluid moving machinery. First one is positive displacement machines, and the second category is centrifugal action machines. So positive displacement means that they apply a direct force on the fluid, they push the fluid, and centrifugal machines uh, do it in another way. They rotate the fluid such that the fluid moves forward by that centrifugal action. Like fans, like we have this ceiling fan, it is rotating and the air gets pushed downwards because of that centrifugal motion. Because the fan blades are specially designed so that that centrifugal force is converted into this straight motion of the air downwards. Okay, so this categorization, fans, blowers, and compressors is as follows. Fans are generally low speed machines. Blowers are slightly higher speed devices. So they are divided based on the pressures that they generate across the blades. So fans generate very less pressure difference. It may be zero point 0.1 or zero point 0.2 atmospheres or even low. And this is generally used to discharge large volumes of gases to large spaces, like in a room, a hall, something like that. Or there can be big fans also, that is also possible. And flow can be considered to be incompressible when there is a fan involved. So flow of air in a room can be considered to be incompressible. Although there is some compressibility to the air, but still because the pressure differences are not so large, therefore density differences are also not so large. Now coming to the blowers, they generate pressure differences or pressures on their outlet up to 2 atmosphere. So inlet is generally considered at 1 atmosphere here. So they can generate pressures up to twice of it. And compressors can generate pressures from 2 to 1000 atmospheres depending on the type of compressor. For example, these compressors that you have on cycle shops or car shops from which they fill the air in the tire. So those compressors, first you have to fill the air in that compressor, that tank. So you need that device compressor which runs and it passes air. It takes the air from the atmosphere and fills it to the tank. So there is a pressure difference between the tank and the atmosphere, and the compressor has to work to force that air into the tank. So there is a pressure difference across that machine compressor, and that is the pressure that we are talking about here. The pressure difference can range from uh, 2 to 1000 atmosphere, and flow has to be considered to be compressible in blowers and compressors because of the large density changes across the device. Okay. Is there any question up to this point? Okay. Now coming to the pumps, hydraulic pumps. There can be pumps for gases, or liquids. So we are talking about hydraulic pumps now for liquids. So density of the fluid to be pumped is almost constant and it is large in case of hydraulic pumps. Pressure differences are also significant. Um, they may be more than 1 atmosphere, 2 atmosphere. And heavy construction is required for these devices. You might have seen pumps at your home also, or in this institute also. You have near AB, between AB1 and AB2, you have a lot of pumps in the open. So you can apply Bernoulli's equation between points A and B that we have done in the last class. And we wrote the expression for WP and the work. So WP is the work given to the pump, work done on the pump, and then you have some uh, pressure added to the outlet, which can be expressed as the work done by the pump. So we wrote this expression in the last class, okay, and we had this efficiency of the pump defined in the last class as well. This we have already done. Okay. Now in the PDF that I have sent to you, there is a concept, there is a term called NPSH. The full form of it is net positive suction head. So we are talking about the suction side of the pump, that is the inlet side, and we are saying net positive suction head. What that means is that it is required for the pressure to be positive. What pressure? So it is this pressure difference that we are talking about here. Pressure at the surface of the reservoir. So if you go back here, it is this A prime, this dot that you can see here. Okay, minus PV. PV is the vapor pressure of the liquid divided by the density and divided by gravity, which gives you um, H by gravity. Okay, and minus the loss in the suction line to the pump. So from reservoir to the pump, whatever are the losses in this pipe, and then minus its head ZA, where the pump is kept. So why this should be positive? So this should be greater than or equal to 0. Okay, and why is that? We discussed this term cavitation in some earlier classes. This can be considered to be a kind of boiling, where boiling occurs at room temperature. And why does that occur? Because of a pressure loss. Okay, if the pressure is equal to atmospheric pressure, if the vapor pressure is equal to atmospheric pressure, then the liquid can convert to vapor at that particular temperature. All right. So this vapor pressure at this temperature where the pump is kept, if that matches with the pressure at the pump, then the liquid will cavitate and it will generate vapor bubbles. And when they implode, they cause damage to the pump and the line also. And there are heavy oscillations in the pipe, in the flow, which can damage the pump, damage the line, and reduce the efficiency of the pump as well. So we don't want that to happen. Therefore, we want to keep a net positive suction head. That's the concept behind it. And you can read more about it in the PDF that I shared. Okay. Yeah. So now we'll talk about positive displacement pumps. How many of you have seen something like this? How many of you know about a piston cylinder engine? that we discussed in the first class actually. Can you please write in the chat window if you are familiar with this? Okay. So when we discussed this piston cylinder arrangement in the first class, that was for an engine. What an engine does is uh, it has some fuel, it gets some energy, it converts it to work. Okay. Here, so the piston is driven by the energy of the fuel, which rotates the crankshaft, and you get some work out of it. But here in pump, what we are doing is we are providing work to this piston. We are moving the piston, okay, by working upon it, and it is compressing the air. It is working on this fluid inside this cylinder. That's the difference between engine and pump. So it is similar to an engine. You have this inlet valve here. Inlet valve opens, some air comes in, then inlet valve closes so that no air can go back or no fluid can go back in the inlet region, and the outlet valve opens and the piston goes up and it sends the air or fluid, whatever is inside the cylinder chamber, to the outlet. And then again outlet valve closes, piston goes down, inlet valve opens, it pulls the air in, and then there is some air to push back again into the outlet region. So that's how this positive displacement pump works. This is one kind of positive displacement pump, which is the piston pump. The maximum discharge pressure is 50 atmosphere. This is some approximate value that is given. It contains a piston in the cylindrical space. There are other kinds of positive displacement pumps, such as plunger pumps. A plunger is just a disc kind of thing, not a piston. Um, and there is a different mechanism there. There are several pistons connected to that plunger. So the maximum pressure is 1500 atmosphere or more. There are diaphragm pumps, in which case there is a flexible diaphragm instead of this piston here, and it can deform. So when there is this inlet cycle where the air comes from the inlet, it goes down. So this shaft pulls it down so that it deforms in a concave up shape, so that there is more area inside this, more volume created inside this cylindrical section. And then again it deforms, it becomes convex up so that the air can be pushed to the outlet section. So for diaphragm pump, the maximum discharge pressure is about 100 atmosphere. Now you can see the differences between these. In a piston pump, there has to be very close tolerance between the piston and the cylinder wall, because otherwise the air or the fluid will leak to the sides of this piston. That's why this maximum discharge pressure is less in this case, 50 atmosphere. But for a diaphragm pump, uh, everything is closed, so there is no possibility of any leakage from the surroundings. Okay. There are no moving parts as such. It is just a diaphragm which is deforming. So you don't need any seals like in the piston pump or diaphragm pump or plunger pump. Okay. Is there any question up to this point? Now these kinds of pumps, another category is rotary pump. So this is different from a centrifugal pump. There's a different term here, rotary, which means that they rotate the fluid rotates with them and it goes to the outlet. Basically, it is not because of centrifugal action that the fluid is moving. It is just rotating in this cavity and moving. So as you can see, there are these two gears. This is also known as external gear pump, this particular rotary pump here. There is inlet. This is the drive gear, okay, which is connected to a engine which can drive it. The work is done upon it, and these two gears are meshed so that the other gear moves because of this gear. And you can see there is perfect meshing between the teeth of the gear of both the gears. So there is no, or there is very little leakage between these two gears. Okay, so that there is no backflow from the outlet to the inlet. There is only one way flow from the inlet to the outlet, and you can see how the flow happens. There are other kinds of rotary pumps, for example, internal gear pump, vane pumps, and so on, which are not shown here. These are mainly used for precise metering. So you have some space here between the two gear teeth, okay, that you know beforehand. So you know the rotation rate of these gears, and from that you can calculate how much fluid will go to the outlet per unit time precisely. And generally these are pulseless, so there is no pulsation in the outlet like in the displacement pumps where you have pulsating outlet. Once the outlet valve closes, then it reopens and so on. So there is pulsation in the pressure at the outlet, but in these kinds of pumps, rotary pumps, there is very less pulsation. All right, and it works best with viscous liquids. Now this category of pumps, centrifugal pumps, these are the most common for household purposes for water. So you can see this is the suction perpendicular to the pump, and then this is discharge tangential to it. The water, I'll use the word water because generally it is used for water. It may be used for other kinds of fluids as well. So from the suction line, this fluid comes in, generally water. Then these are vanes. This is known as impeller. It rotates, it gives the fluid a centrifugal motion so that the fluid gets thrown outwards, and then this design is known as volute. It is like a spiral casing where the fluid goes outwards away from the veins and then discharges from this outlet. Okay, is there any question here? So with centrifugal pumps, there is a problem. To solve that problem, priming is required. You may have this experience, or you might have heard this, that if a pump goes dry at home, let's say there is air in the inlet pipe, there is no water, then you need to fill water in the inlet side for the pump to run again. Otherwise, it won't work properly. So this process of refilling the inlet with water is known as priming of the pump. So it requires removing all the entrapped air from the suction line and the pump. So the entire pump has to be filled with the water or filled with that particular fluid. Otherwise, it will not work properly. Okay, so the reason is written here. Because the centrifugal pump cannot pull the liquid, it only pushes the incoming liquid outwards. So if there is no liquid in the pump, it cannot push anything outwards. It cannot provide this rotational motion to any liquid for it to go in this discharge section. The fan or the impeller will just keep rotating here. It will not be able to pull any liquid in. The air inside this volute will just keep on rotating here. It doesn't apply any force, any suction pressure. It is only the action of this outgoing liquid that pulls more liquid inside. Okay, is that clear? If there is any question, you can ask now.
So the normal pumps we use in our homes, like to fill up the water tank in our houses, this centrifugal pumps are used. Oh.
I'm not able to hear you properly. Can
So
you please
actually,
repeat?
I'm asking that the normally the houses, common houses, the pumps are used to fill up the tank. This centrifugal pumps are used or others?
Yeah. So normally at homes, these kind of pumps are used, centrifugal. These are the most common ones. Even in the coolers, the pumps that you use at home, you have these coolers, right? Which throw air, which throw water um, on this net that we have with grass, and then that cools the room. So that kind of pump, desert cooler pump, that is centrifugal pump, and the pump that you use to push the water to a tank above the building, that is also a centrifugal pump.
Okay.
Yeah. So all of these different kinds of pumps, you have a wide variety of pumps. You might have heard about submersible pumps. So they are also centrifugal pumps. They are already dipped inside the water, so they don't require priming. That is already taken care of. But when you have pump outside water tank, that requires priming if it goes dry. So the solution just is to refill it, to fill the pump and the inlet pipe. So with the water again, it will run. Okay. On the other hand, positive displacement pumps do not require priming because they actually pull the liquid in. You can see here. So when the piston goes down, it pulls. There is a vacuum created here, okay, or the low pressure region is created here, which pulls the liquid in. So even if there is air in this section, that will be pulled inside, and the liquid will also be pulled inside. So positive displacement pumps don't have this kind of problem. And in the PDF that I shared, there are performance characteristic curves, which can be seen here. So you can calculate from the Bernoulli equation this pressure head created by the pump at the outlet, and this is the actual pressure head that you get from the experiment, and this is versus the flow rate. Q is the flow rate. So all these three curves are versus flow rate, and these are different things plotted here: head, power, and efficiency. Okay, so you can see efficiency decreases after some flow rate. So okay, so this you can read again in the PDF, and you can solve the assignment. Then after that, if it is needed, we can discuss again. So fluid moving machinery part is done. Now we needed to discuss this part, mechanism of size reduction. Uh, So mechanical operations, size reduction of solids. This was one of the remaining topics. Why do we need to reduce the size of the solids? To maybe take something out of the solids, maybe some minerals are there, some important material is there, for example gold, or even to increase the surface area, mm, surface area per unit volume, so that the reactions are easier to carry out. For example, if you want to burn coal in a hydrothermal power plant, uh, not hydrothermal, in a thermal power plant, there you need large surface area of coal so that it can burn faster. Okay. Or separation of entrapped particles that we have already discussed, gold mining and so on, or metal mining. So you require them to convert from coarse to fine. There may be several different grades of how coarse the particles are. This requires very high energy input with size reduction of solids. There are different kinds of processes by which you can reduce the size: compression, impact, attrition, or cutting. These are slightly different, each of them. So as written here, 99% of the energy goes in noise, heat, and running cost of the equipment, electricity, and so on. Only 1% goes in creating new surface area. So you can see how inefficient this process is. And energy input goes up significantly for even finer reduction. So from fine particles to powder, if you want to make, the energy input goes up significantly. Only about 0.1 or 0.01% energy goes into creating new surface area. So this is about size reduction. Equipment, these are handheld equipment. Okay. Mortar and pestle and so on. And this is something industrial. So when there is mining, you have big chunks of rocks. This one is known as a jaw crusher. So you can see this is a jaw. You have this green side and this red side. Okay. There is no green and red, but I'm just telling you because this is what the figure shows here. These are two plates and these are serrated, and this is a shaft that rotates. This is a wheel, flywheel that rotates, and this jaw goes forward and backward. Okay, and as you can see, because of this converging section, these rocks will come down and they will slowly be reduced to medium sized particles or fine particles depending on the size of the outlet. Okay, these are some specifics. Manganese steel is used on jaw faces. It has to be hard. It should not break also. It should be harder than the rock. So types of crushers according to the position about which the jaw rotates. There is Blake crusher, Dodge crusher, and universal crusher. Alright. So there has to be some axis about which this will rotate. So depending on where that is, these three kinds of crushers are there in the industry. This is known as gyratory crusher. This is the central axis, and you can see this is slightly off axis. This is not passing through the center of this blue region here. Okay. This is a cross-sectional view of this crusher. This is actually a whole conical section. Okay. This is a cone inverted. And there is this motor which rotates it. It is off axis. Therefore, you can imagine that it will hit on one side of it it will be closer to this one at this moment, and then at another moment it will be closer to another wall. Okay, it may be slightly difficult to imagine here, but when you read about it, it will be more clear. These are roll crushers. So these are rolls, two rollers. These are coarse particles, and you get finer particles at the outlet. Coal crushers, yeah. So different kinds of crushers can be customized for different purposes. Coal crushers usually have teeth on the rolls, the extra teeth here, while metal or mineral crushers don't. Okay, and these are less cost effective than cone type of crushers. Gyratory or gyratory are called cone crushers. Now you have grinding for converting fine particles to powder. This may also be slightly hard to imagine in such a short time. You can see that this bottom face, this is again a cross section, vertical section that has been taken here. This is a serrated bottom. This has very high friction. All the fine particles are put inside this mill. This is known as a mill. So this is called hammer mill. Where are the hammers? These things. These four hammers are there, which can swing. Okay, as this central disc rotates. And this swinging causes the particles to break against this lining of this container. Okay, and then there is a mesh here through which some particles can go down, and you can customize this mesh. You can reduce the mesh size, you can reduce the size of the pores in that mesh so that the desired particle size comes out of this mill, so that you get powder basically. This is another kind of mill which is known as a ball mill. These black colored circles that you see here, filled circles, these are steel balls, high chromium steel. Okay, and you put some particles here which need to be uh, reduced in size, and it is just this mill, this cylindrical, as you can see here. It is rotated like this, and because of the friction between the container and other particles, they go up slightly on this side and then they fall again. And because of this, these falling balls on on this on these particles, they break down into smaller pieces. This is how this action takes place. But there is one important thing here. There is some critical speed of this mill, beyond which, if you rotate this mill, this grinding action will not occur. So that speed is known as this critical speed, and the formula is given by this. This is an analytical formula which you can also derive. Now, who can explain why there is some limit to the speed of this mill? Can somebody explain why there has to be a limit to the speed? What happens if you rotate it at a very high speed? Why will this grinding action not take place? Not take place?
So then balls will stay at the surface only, they will not come down.
Yeah, that is correct. Yeah. So because of this centrifugal force, they will just stick to the sides. They will not come down. Okay. And ball mills are usually operated at around 75% of this critical speed. Okay. Then there is something called sieving. After all of this is done, there are different sieves you can use to get the desired shape, desired size, not shape. Then there is more to mechanism of size reduction, how exactly a particle breaks down, and what are the limitations to size reduction. Size reduction depends on several properties such as compressive strength of particles, brittleness, stickiness. Okay. If let's say there is some material which forms agglomerates, then if you grind it, the particles which have already broken down, they may again come together and form a bigger particle. So it may not be fruitful after some limit to grind it even further. Okay. So like that, there are several things to discuss here, but let us discuss this first. This is for grinding of coal. The plot here shows particle diameter on the x-axis in micrometers. These are revolutions of hammer mill or ball mill. This is from a particular kind of mill, and this is mass per micrometer, which is shown here, the particle diameter. So the first curve that you see here, it goes from 600 to 1600 micrometers. So the minimum particle size in that lot, which was fed into this mill, in this mill, is 600 microns, and the maximum size is 1600 microns. And maximum number of particles have this size somewhere here, which is about 900 or 1000 microns. Okay. Now after okay, these are 0, it starts from here, and then at 200 revolutions, after 200 revolutions, you can see this curve. Okay, this is drawn in 3D, so this is not a negative value, it is still positive. You can see two prominent sizes here, two peaks. One is here and the other is somewhere here. Then again at 400 revolutions, you can see one peak is here which is growing. What that means is that many particles are of that size. What size is that? About 50 or 100 microns. Okay. And then here there is another peak which is at about 350 or something, or 400 microns. So you get these two modes. Maximum particles like to lie in these two zones, these two diameters. And then finally this second mode disappears, and after some 950 revolutions you get this kind of curve, which means that the maximum diameter is about 220 or something, and the minimum diameter is close to 0. So it is very fine powder. The minimum diameter is very small. And most of the particles are here. This shows the mass. The maximum mass is concentrated here. That is at about 50 microns. And if you increase the number of revolutions, there is little change in the maximum diameter of the particles that you can see from this curve. But there are more number of particles that you get at that size. Okay. and after this there is little change in this curve. So this is known as the first mode. First mode, that is this peak, the first peak. Sorry, that is not the first mode. That is the second mode here, which is the persistent mode that always remains throughout the grinding process. And the first mode is this lower peak, which disappears after some time. That is known as the transitory mode. So this is something special about grinding. So particularly for grinding of coal, these two modes appear. The first mode disappears, and the second mode, that is called the persistent mode, it keeps on developing. So more and more particles go there in that range. Okay. And there is something called grind limit, which is there for a particular material and a particular machine. So for this particular machine and this material, there is a grind limit. That is, there is a size limit to which you can grind the material. After that, even if you continue grinding, it will not change the particle size anymore. Okay, there are many more things here, but we'll discuss only up to this. I will send you these slides or the reading material related to this. Okay, so that's all. If you have any questions, you can ask. Okay. Okay, then that's all. Thank you.